Okay, so I guess we're ready to proceed. So remember that the last thing that we discussed was the so-called Friedmann equation, right? So the general Einstein equation, remember, takes this form where the left-hand side is something that contains second derivatives of the metric, and the right-hand side is the source term for gravity, which now includes not just energy density, but for example also pressure. We also discussed the fact that in a homogeneous and isotropic universe, one can write the stress energy tensor in a particularly simple way because it can contain only diagonal terms. All the off-diagonal terms, let's just write it out again. Remember, so the diagonal terms contain the local energy density in the 0, 0 component and the pressure along the three Cartesian coordinates in the spatial directions. And all the other terms correspond to flows of various quantities. For example, up here you will have energy flow along the x, y, and z direction, and down here you will have momentum flow in various directions. And since we have a universe that's homogeneous and isotropic, you must always have zero net flow of all these quantities. And that means that we can explicitly put all the off-diagonal terms to zero. But that also means that the whole Einstein equation, which really contains, at least at face value, 10 different independent equations, can contain only two, because not only are there only diagonal terms, but all the spatial diagonal terms must be identical. Again, you cannot have different pressure in different directions if you're an observer at rest in the system. So these are identical. That means there are only two quantities that enter the stress energy tensor, the local energy density and the local pressure in the system. That's all there is to it. And you can see already here that means there's one equation related to the 0, 0 component and another independent equation related to the spatial components of the Einstein equation. Now, the one that we normally talk about in cosmology is the 0, 0 component. So let's just write that out. And like I talked about in the last video, what you get is a time differentiation of the scale factor, and this quantity is normally what we refer to as the Hubble parameter, so that's the logarithmic derivative of the scale factor, which is the Hubble parameter. So that's what quantifies the expansion of the universe. Then on the right-hand side, of course, not surprisingly, we get the local energy density for this 0, 0 component. And one might think it should just be like this, but in fact you have to divide by 3, and that number 3 actually comes from the terms on the left-hand side. So it's just that when you write the Friedmann equation, you tend to want to isolate the A dot term here. And here we, as it turns out, get one additional term which has to do with the possible spatial curvature of the metric. And you see the curvature radius also appears here. So that's the fundamental differential equation that you'd have to solve if you want to know how the universe expands or contracts. And of course, we are not yet really equipped to solve this equation, right? Because we don't know, for example, how the energy density behaves as a function of scale factor. So that's something that still remains to be done. Before we do that, let's just try and massage the Friedmann equation a little bit and see if we can get a little bit of extra information out of it before we start thinking about actual solutions to it. So let's start again from the Friedmann equation, and let's call this again h squared. So let's divide through by h squared. So that means I get a 1 like this. Then I could isolate this term, the curvature term. So then I'd get and then you can see at least one interesting property, and that is that the sign of the curvature must be determined by whatever you put into the universe. It must depend on the local energy density in the system. And since the local energy density is the same in all locations, it must depend on the energy density in the universe. So we can see, for example, that if I fine-tune rho such that it is exactly 3h squared divided by 8 pi t, then this term becomes identical to 1, and that means I have a 0 here. So this energy density means that I get a kappa of 0. So I have no curvature. We can also see if rho is larger than this number, then kappa must be positive, because what I have on the right hand side is a positive number, and whatever I have down here is positive definite, and that means that the only possible solution I can have is to have kappa equal to +1. And if rho is less than this number, then the opposite applies, then kappa must be -1. And therefore in cosmology, one normally defines what is called the critical density, meaning the density which is needed for the curvature to be exactly 0. And then one more definition is usually made, and that is the so-called density parameter, omega. So that's just defined to be the actual energy density divided by the critical density. So then you see if omega is equal to 1, then kappa is 0. If omega is larger than 1, then kappa must be +1. And indeed, if it is less than 1, then kappa must be equal to -1. So then we have a clear distinction in the curvature of these models, and it depends only on the local energy density in the system. And so there's a one-to-one correspondence between the energy density in the universe and the curvature of the universe. So that's at least always interesting to see that you get this dependence. Of course, we are not yet any closer to an actual solution to the Friedmann equation, so that still remains. But this parameter you will see over and over and over again in cosmology, because again it's the, if you want, fundamental parameter that we're dealing with. Okay, so let's now proceed. So the next question to be addressed is what is the evolution of the energy density as a function of scale factor, and how would one go about solving that? So actually there are two different ways that one could do it. The one way is to take the Friedmann equation and take the corresponding spatial equation for the scale factor that you get out of the Einstein equation. And using that, you can actually derive an equation for how the energy density evolves. But you can also do it another way. So just like in normal Newtonian physics and in all branches of physics, we have fundamental conservation laws that apply. And the question is, what is the fundamental conservation equation that you have in general relativity? So one fundamental conservation equation is stress energy conservation. And one can write this in a slightly weird way. So for example, if you take, now I just write them with both indices above. Again, remember, same thing, right? It's just that you can lower or raise the indices by applying the metric tensor. So it's not identical to the one with lowered indices, but it's related through various multiplications with either the metric tensor raised or lowered. Okay, so as it turns out, there's a fundamental conservation law that can be written in this slightly obscure way. So in GR, one normally uses either a comma or a semicolon to denominate derivatives. So for example, if I were to write something like this and then comma nu, that simply implies I take the partial derivative with respect to coordinate nu. And of course now I have an upper and a lower index here, which means I must sum over them, right? So then I would have to sum over all possible values of nu if I want to calculate this quantity. The semicolon is a similar thing. The only thing is that I have to take into account how the metric changes with space and time when I do this derivative. So I have to factor in, so this would be true in a Euclidean static coordinate system, but since I have an evolving, if you want, coordinate system, I cannot do a derivative like this and expect it to be conserved because the metric can change both as a function of space and time. So instead, one can write a similar equation but with a semicolon. And a semicolon contains derivatives of the metric. So it basically contains all the terms that are needed to understand how the metric changes. So the coordinate system you're using to do the derivative changes as a function of space and time, and that has to be factored in. And this is called the covariant. The covariant derivative. And those of you who had experience, for example, in field theory and particle physics, you'll know it's the same kind of language that one uses. So instead of having simple coordinate derivatives, one can go in a free theory, a theory without interactions. One can go to a theory with interactions by appropriately changing these derivatives to factor in the interaction. That's another use of a covariant derivative. The same thing applies here. And I'll show you in a minute what that looks like. First, also notice, of course, that this equation actually contains 4 different scalar equations. And that's maybe not very surprising because actually this is just another way of writing energy and momentum conservation in the stress energy tensor. So somehow the zero component must correspond to energy conservation, and the 3 spatial components must correspond to momentum conservation. And indeed this is also true in normal classical fluid mechanics, where you also, like I said in the last video, where you also have the stress energy tensor. So actually this equation, when you look at it a little bit more closely, contains the continuity equation. So that's the conservation. In normal fluid mechanics, that's the mass conservation law. But here is the energy conservation law. And it also contains the Euler equation, which is the momentum conservation law. So that's the one that normally tells you, if you have some element of fluid, how does it behave under the influence of whatever force you have available in the system and whatever pressure you have available in the system. Those of you who had a course in stellar physics will know the Euler equation in a stationary form as the equation of hydrostatic equilibrium. Again, it's the same equation, it's just in a different setting. So really, this thing is the energy and momentum conservation equation. So let's try and see what that actually looks like in Friedman-Robertson-Walker cosmology, so in homogeneous and isotropic cosmology. Well, naively, maybe you would think that since everywhere is the same, these equations should be completely trivial. However, that's not the case because everything is not the same along all directions. We have the time direction where you can actually have something that evolves. So let's try specifically and look at the zero component of this energy conservation or energy momentum conservation equation. So the zero component must contain energy conservation in some form. So let's write it out. So when I do this derivative, so let's write it out. That would be the normal coordinate derivative, right? Of the zero component. But then I get additional terms, like I said before, because I also need to do differentiations of the metric tensor. And those can be quantified, not surprisingly, in the form of these Christoffel symbols. So actually what I get out is something that looks like this. Where again, remember, I have to sum over the index mu, and I have to sum over the index alpha. So altogether I get a scalar equation out. But I have two new terms that I need to evaluate in order to actually see what this equation looks like in normal coordinate language. So the first term, the simple derivative here, that we can do without even calculating anything. So remember, the stress energy tensor is a diagonal tensor. That means that mu has to be 0 explicitly, otherwise this doesn't work. So that means I have to differentiate the 0, 0 component of the stress energy tensor with respect to the 0 coordinate, which is time. Right, so this would give me, and now of course I have to remember, I didn't write it anywhere, but I have to remember there's a minus sign, which I now realize I might not have written in the last video, but it's minus rho and then PPP, and you can see that also in the notes and in Dodelson, but I think I might have forgotten to write it out. Okay, but this is the first term. Then the second term, if you actually write that out, do all the, here you can see you need to have alpha equal to 0, and altogether I get something that looks like this. And then the final term, that is this one, which you can evaluate to be, and I mean this surely you can do for yourself, it's not very problematic. You have all the Christoffel symbols available in Dodelson, you just have to look them up and do the proper summations, and then you'll get this out. So I have 3 terms and they have to sum to 0. So let's write it out. So what it actually says, if I now take away the minus sign and multiply through with minus 1, I get this equation here. And this is the energy conservation equation. Of course, you can also already see that if the scale factor is constant, meaning I'm in a static space, then this term vanishes, and then indeed it is completely trivial, right? Because then it says that rho dot is equal to 0. Not surprisingly, the energy density cannot change in a static space that is everywhere the same. So that possibility is contained. But since I have a time evolution, I can actually change the energy density. And it's not in a completely trivial way. You see there's a pressure term appearing here. And that means the evolution of energy density must depend on the pressure of whatever component I'm looking at. And since pressure, for example, is high for a relativistic gas, a gas of photons, for example, then that must change in a different way compared to a gas of non-relativistic particles where pressure is low. So we'll see that in a minute. Indeed, that is true. Now, of course, one can also explicitly check all the spatial components if one wanted. So let's just briefly write out what it would look like. So now I have an I component, which remember is a spatial. That's 1, 2, or 3. Like this. Oops, and then a minus sign, of course. Okay, and again, it doesn't take long to realize that this is indeed 0, because now, for example, mu must be 1, 2, or 3. It cannot be 0. But that means I have to do the coordinate derivative with respect to a spatial coordinate. But that must be 0, right? Because pressure and energy density is everywhere the same. So that for sure is 0. And again, one can evaluate these terms, and I get big fat zeros here. So that just tells you that yes, indeed, the Euler equation in a homogeneous and isotropic universe is completely trivial. It just says that 0 is equal to 0, right? Because you have no flow of anything anywhere. Once we get to cosmological perturbation theory, this is no longer true, because in that case, you have different energy densities and pressures in different locations, and then this becomes non-trivial, and indeed it becomes crucial to do the proper Euler equation and solve it in order to do these perturbation calculations. So that's a complication that we'll treat when we get to it. The final thing about this energy conservation equation then one might notice, that is that you can actually write it in a somewhat suggestive form. So you can actually write this in the form, if we assume that everything is continuous and differentiable, you can write it on differential form like this, where the total energy in some volume, well, that's the energy density times the volume by definition. And then, of course, one can calculate dE and dV. So V, for example, the volume, well, that must be some normalization volume times the scale factor cubed. What else could it be? And then you can do the differentials over there, and then you will very quickly realize that you can put it on this form here. So that's quite neat, because it shows us that the energy conservation equation, not very surprisingly, is equivalent to the first law of thermodynamics. And that, of course, must be true, because the first law of thermodynamics is indeed a conservation equation for energy. Now, of course, you'll also notice that there's a term missing here. So usually in thermodynamics, we also have the non-adiabatic heat term, right? We have this dq term, which doesn't appear here. So somehow that's missing. And the question is, why does that happen? Well, it kind of happens because we cheated slightly. What I did was I wrote out, remember, the stress energy tensor, and now I put the minus sign there. I wrote it out in this particular form and claimed that this is the most general case. In fact, it's not. This is the stress energy tensor of what is known as a perfect fluid. And in this language, a perfect fluid means an adiabatic fluid. And for adiabatic systems, of course, I have no entropy generation and I have no dq term. So by construction, it doesn't appear. And then one might wonder, is that really a good approximation in our universe? And the answer is that yes, in almost all circumstances, it's a fantastic approximation. It's extremely close to being true. So in reality, one would have extra terms appearing here due to what is known as bulk viscosity. That's the only term that can survive in a homogeneous and isotropic system. So that generates heat. And if you want a case where that actually applies, it's if you have the decay of some heavy particle into lighter particles. That generates entropy. And intuitively that makes sense, right? Because a heavy particle will be very non-relativistic, that has very low entropy. Then it decays into radiation. Radiation has extremely high entropy. So you generate entropy through that decay if it's out of equilibrium. And indeed it will be out of equilibrium if the mother particle is heavy. So that's one case, and it's one case that actually does apply to our universe, namely at the end of the inflation phase in the extremely early universe. All the entropy, presumably, that we see in the entire universe, basically, is generated at that instant in the very early universe. After that, entropy is to an extremely good approximation conserved at all times, whatever entropy has been generated in our entire history of the universe is completely negligible. Essentially, all entropy in the entire universe now sits in the cosmic microwave background radiation and in the corresponding neutrino background radiation. And all the entropy that we see here on Earth and everywhere else is just a minute perturbation on top of that. So yes, indeed, for all practical purposes during almost the entire course, we can safely assume that this dq term is 0 and that this equation holds. And that means that now we're actually in a position to start solving the Friedmann equation. The only thing that we're now missing is the pressure, what to do about that. And put another way, what we actually need, same thing, for example, as if you want to solve the equations of stellar structure and evolution, then also you need the equation of state of whatever plasma that you're looking at, because it provides information on the pressure of the system. So what we really need is this function here, pressure, as a function of energy density. So that's the next step before we can actually do real solutions to the Friedmann equation.